Hi everyone, my name is Leo. Congratulations on everyone managing to stay until the last session. I'm going to talk about Powdr, what it does, what it is, what's around it. So Powdr is a modular stack for zkVMs. What does that mean? It's a compiler framework that aims at providing many front-end to many back-end architecture. And so why did we decide on doing something like this? So if you look at the state of current zkVM tooling, there are kind of like two camps. One being probably the most common one, which is groups or people that write circuits by hand. And a lot of these VMs they are written as like Halo 2 circuits, for example, which is written using a programmatic Rust API or things like this. And there's quite a few projects using this approach for rollouts, for L2s, for coprocessors, for different things. And the other camp being more language-based teams, where you would see, for example, Polygon zkVM or Polygon Maiden, where you'll have a constraints language, which in this example would be PIL, and then you have an assembly language on top, which defines a lot of the instructions from the EVM, for example, in the case of the Polygon zkVM, and then you have a prover underneath that. And in our case, we believe the second one is a lot more future-proof, and it just basically is the future. And while the first is basically enables most of the projects we see nowadays, it allows for a lot of optimizations, a lot of handwritten things. We do believe that the second one is a lot more flexible and will power a lot of the upcoming projects that we'll see in the future. So what Powdr allows it to do is to define zkVMs. So it's one or even two levels higher in the abstraction stack compared to a lot of the projects that are language-based, in which instead of defining a VM itself in a simple language, you get a language to define VMs yourself. And these VMs can be pretty much anything. Can be an EVM, can be RISC-V, can be LLVM, can be basically anything. And this allows for modular machines. These modular machines basically meaning low-level coprocessors or Merkle trees, which are kind of like in between, or even higher-level things. And the main advantages of doing all these things in a language-based approach is that it's much easier to build, test, audit, and improve over time when you're doing iterations. And as the proof of concept, the first VM we wrote was the RISC-V implementation, which takes about 300 lines in our assembly language. And ValidaVM, which is actually in progress and was and we're expected to be very similar, in which you could actually reuse a lot of the code in the Powdr assembly. If we zoom out a little bit, this is kind of what the architecture of Powdr looks like. So we have all the bits in the middle are the compiler. So what I mentioned before with being a many front end to many back end is what you see here. The many to many are the blue bits. And we can define a lot of different VMs in Powdr assembly, those being, for example, RISC-V, LLVM, WASM, EVM, Prolog, JVM, whatever you want to write. And whichever language is compiled to these VMs, they can be used as front-end languages in Powdr. So then JavaScript, C++, Rust, Solidity, again, Prolog, that's what I would like to have, and anything else. So the VM itself is also part of the input because it's part of the language. There's nothing built in. You write the VM yourself, and then, of course, this becomes kind of like a library item. Within the compiler, there are also different levels of abstractions and different languages. So at that point, what we have is an assembly language that allows you to define machines, instructions, and bytecode. That gets compiled after different passes, different static analysis, security checks, this kind of things. Gets compiled to a low-level constraint language, which we also call PIL. It's this specific PIL started as an extension to Polygon's PIL. PIL meaning polynomial identity language. And we made a few changes, and then in the end, we ended up writing our own version. And what happens then is that we have constant generation, witness generation, an optimizer on top of that. And then finally, we end up with basically only constraints. And then at that point, we can basically transform those constraints into basically any arithmetization that roughly supports the same type of constraints. So currently, we have Halo 2 and eStark as the backends we support directly in the compiler. Supernova is being written at the moment, and Lasso is something obviously came out very recently. But we're highly interested in that because the machines we write they rely very heavily on lookups as well. So I think this could make sense once we find out how to use it. Oh. So just to give you an example of a snippet of what this language looks like, the syntax is still a bit rough. We're always iterating and improving on it. But the basic idea is that if you're writing a VM, you want to have the basic thing. So you want to have registers, you want to have instructions, and you want to be able to write code. And that's basically what you see here. So this is a very simple VM that has 3 registers, and 2 of them are annotated with specific flags. One of them is a PC register, the other one is an assignment register with the arrow, and A is a general purpose register. We have only one instruction that allows us to assert that a certain register is 0. And when you see x equals 0 over there, that's not an assignment, that's a constraint. So inside instructions, what we have are constraints, which have the same language as the low-level constraint language that it gets compiled to afterwards. Then we have a main function, which basically looks like any assembly you would see in AT&T or LLVM or different types of assemblies. So we assign 0 to A, we assert, oh, it should be A instead of 0. That A is 0, and then that's the end of our machine. But what if we want to do more complicated things? Like what if you want to write a hash function in our machine? Well, we'd build an instruction called hash that basically hashes something, gives you something. But how do we write this? Because if you want to write this as machine code, this would probably be quite wasteful because you're spending computation to build this hash. And what a lot of people do, they have low-level optimized circuits that compute these kind of things. Well, in this case, you do exactly that. So we'd build a machine hasher that doesn't have any registers, doesn't have any bytecode. It only has constraints. So this is as low level as it gets. So you're basically doing the same as writing a specialized circuit for hashing. And in this case, this will become part of a library, for example, that a lot of people can use. And this hasher machine, you can go back and use it in your main machine. So you just say, well, I have my main machine here, which has a program, but I also want to have an instruction hash. And you define the instruction hash, and you say, I'm going to delegate the computation in this instruction hash to my specific hasher. And the advantage of doing this in the language level is that this here in the language on the left-hand side doesn't really specify how this is done. In which case, you could do it via computation, you could do it with constraints. Currently, it's done via lookup. But in the future, this could also be a recursive proof. So the language is already set up for different things like recursion, even in the most granular level. And this is finally what the constraint language looks like. You basically have columns, you have multiplication, addition, lookups, permutations, and this is, for example, some bits from the catcheck. I think it's machine. And as a compiler, it has different compilation passes. So what happens first? The virtual machines, the machine that I just showed, are optimized. They're reduced to simple constraints in the PIL language. Then they're all collected and linked together in a way with the lookups, if you're using submachines and kind of things, into a single PIL object which contains only constraints. Then they're finally optimized. Columns are removed, for example, expressions are simplified, and then finally gets into the different backends. The execution process is very simple. Currently, there's automatic witness generation. You only have to give the prover inputs if your program needs prover inputs. But we know that a lot of optimized coprocessors will need custom witness generation, and this is something we're currently working on. As I mentioned before, these are the backends we currently have or are working on. So the Halo 2 backend works directly including aggregation and EVM verification. The eStark backend, we use the star key library, not from Polygon 0, but from Eigenlabs, because they actually implemented the same eStark as Polygon Hermes on the zkVM, meaning that they added functionality, they added lookup and permutation arguments to the prover itself. And Supernova, we have a collaboration with Ming from PSE, who's writing a Supernova backend directly for the assembly level instructions and not for the constraints level, which looks super cool. A few of the applications we have in mind and or are working on are these. Some of these are pretty obvious. So doing things like zkRISC-V or zkWASM are things that other groups are also doing. And these enable you to prove execution of any program, of any established language, which you've seen before: Rust, C++, Go, JavaScript, any of the things that people already use to write everything we use every day. zkVM is another obvious one. Of course, there are different zkVMs already implemented, but writing one in Powdr would allow us to have Something with a lot more would be kind of like higher level, easier to audit, easier to read, and easier to optimize and extend. Say, for example, if L2 start adding different functionalities that the L1 doesn't have yet. Another big use case we're looking into is L1 data, so type 1 rollups, for example, or if you're trying to do arbitrary computation, so not necessarily a specific only off-chain computation, but you still want to use L1 data. So this is something that has a really big use case and we're also working on. And then last but not least, optimize zkVMs. So if you're a team, like if you're a VM builder, this is then the next branch where you would use Powdr not for the RISC-V or WASM high-level programs, but to build your own VM, to design your own VM and spec it out in the assembly language and then only focus on the prover, and it would benefit from the entire compiler stack. All right, so I have 9 minutes left, so I'm going to attempt a demo and an ambitious demo, and we'll see how far that goes. So what I don't have a mirror thing, so I'm just going to turn around. So the first thing I'm going to run, and I'm going to show you, is a small program written in Powdr assembly itself. It's going to be this program here, which hopefully you can read. I'm not going to go too much in detail, but this is a program that, in the end, it's a VM, which exists just to give us registers we can play with and a few instructions. The program itself is here. What it does is read a sequence of numbers where the input is formed by, you want to prove that you know the sum of a list of numbers. Very simple, but that's what this example does. And then the input is, first, the prover gives the sum they claim is the sum of the list. Then the second input is the length of the list. Then from the third on, it's the list itself. So what our program does, the first thing is read the length of the list into this count register. Then the rest pretty much looks like an assembly program where we have a label start, we have a loop, and we have this jump 0 instruction. So if count is 0, which is the end of the list, we jump all the way to check, where we check that the sum is indeed what the prover said it was. If it's not 0, we read the next item in the list, we accumulate over A, and then decrement a counter, jump back to start, right? And in the end, we have a sum. We see if it's the same as the prover claimed it was, and then end the program. That's basically asserting that this is only going to pass if all the inputs are correct. But what you can notice here, nothing here is built in. So all these instructions, they were defined here using the language itself. So the jump, what jump does, you get a label, and the next PC must be the label that you gave. This is defined in the language. Jump Z does the same thing, conditional on X, the register that you pass, being 0. And assert 0, same thing, and then decrement the counter, same thing. The next count must be count -1, right? So the whole VM is defined in the language itself. There's nothing here that's built in, and the compiler just, that's what gives the most flexibility for the compiler, because this is obviously a very simple VM with 4 instructions, but in the same way, we can build all sorts of VM with the same language. And to run this, it's going to be here somewhere. Okay, so this will run this example, giving as input 6, 3, 1, 2, 3. 1, 2, 3 being the list, the leftmost 3 being the length, and then 6 being the sum. And we're telling it to prove the resulting trace with the eStart backend. Okay, yeah, that was fast. There is a proof, if you believe me enough. These outputs are from the prover. And this was pretty small because obviously the program itself is pretty small. We can do the same thing and tell it to use Halo instead. And here we have to change the field to BN. So currently, before the eStart example is using the Goldilocks field. And here we're going to use BN because of Halo 2. And it is actually a little bit slower. Yeah, it also has to generate the setup and everything, but we also have a proof here with Halo. This is pretty small, so you could, well, maybe not as small as you could prove on chain, but Yeah, so you could also do aggregation, like recursion and aggregation, all sorts of things to make it smaller. Now go into the more ambitious demo. So obviously this was a pretty small example and not something you would do realistically. So other things you can do are, wait, not here. So this is one example of something we could do in Rust. So if you want to make proofs of Rust programs using the RISC-V front end, all you have to do is put an OSTD annotation up there. It needs to be an OSTD for now. Null mango main function, and that's it. That's all you have to do. And then you can write any Rust code in here. So in this example, we're using a tinycat crate, which is not ours, it's a crate that exists. And it's an OSTD crate. So here, basically, we're proving that we know the preimage of a hash, right? And this is going to compile to RISC-V. We get all the assembly RISC-V files, transpile it to Powdr assembly, inject in the RISC-V virtual machine written in Powdr, and then just goes into the same compilation pipeline all the way to a proof. And we can do the same thing here. Yeah, so this will run this. We're passing the crate directory, and then it's going to find the lib file, and then just find the main function and try to prove it. This is going to be a bit longer because the RISC-V. So this is first using cargo itself for the RISC-V compilation of this Rust program. So this is the assembly files from RISC-V, compilation, optimizations, and this is the automated witness generation part, where here we're filling out all the rows. So this is all the unused parts that we have to fill out anyway, but it's obviously a lot faster. We finally get to the end of the trace. We get all the artifacts, and now we're finally creating the proof. This is going to take a while, so I'm going to stop here. And I think I need a bit more RAM than my laptop has to prove this. And if you do Halo 2, it's going to be the same thing. So the thing is, like, up to here, the Halo 2 setup is the same, right? So there's nothing different that we have to do. We do have to change the field, but the compiler code, the compiler pipeline is still the same for any execution trace we try to run. And then from that point, we can basically swap and choose different provers, different backends, and basically reuse all the compiler pipeline that you would for any other use case. Yeah, so let's just try the Halo one. This is going to be a bit slower again because of the BN field, which is the math is a lot slower than Goldilocks. So the witness generation part is going to be slower. This part's the same. Yeah, you can already see it's almost half the speed.
Why use your own pill and not the Polygon one?
We do support the Polygon one in the sense that when we compile our pill, it generates the same artifacts than the Polygon pill, so we can actually use the same prover. The artifacts are literally the same. We changed the pill because there were some things we didn't like in the language itself, in the Polygon pill. For example, the constant columns, they were only declared in pill, but they were not defined in pill. So they were pretty much, you'd rely on an external executor to build the constant polynomials that you were relying on for the constraints inside the pill code. So this is one of the first changes we made our pill, just like you have to define the constants inside pill itself so that the whole thing is self-contained. Yeah, so this is going to generate a Halo 2 proof, if you, again, believe me enough. So, but it's going to take a while, so I'm going to stop here.
Why tries to use the loop?
Sorry?
Why try to use using?
So what happened here is that the actual execution trace, oh shit. The actual execution trace from the Rust program stopped all the way up here somewhere. It stopped here. But because the execution trace in this proof has a static size, we have to fill out the remaining of the program. So in the Rust program, actually, when we link, there's actually an infinite loop here. in the assembly. So there's just like an infinite loop just to fill out the rest of the program. That's actually why this part is so much faster, because it's just copying things around. And this here, you have to ask him.
Things are different in the last
row. Yeah, I'm perfectly out of time. Let me just go back here. Yeah, thank you.